So you reduce the probability, for example, here to 90%, and you distribute the 90% over the remaining classes uniformly. And this is a regularization technique that works quite well in the supervised learning of models. So you can kind of draw some connections between this kind of soft distribution between all the outputs from a trained model compared to label smoothing. So it's not at all very clear, even though we know it definitely works, why taking multiple random initializations and then combining their output work in the first place. So we use exactly the same architecture, 10 or n in general ensembles, as we say, and then we just average their prediction. So in the probability distribution, we just combine the outputs of those models, and this results in a in a much better prediction than any of those 10 or n individual models trained. So this is still a mystery. This is like an example on Cypher 100. This is a paper from Microsoft. So this is the mean and the standard deviation of all these 10 individual models. So 81.51 trained with supervised learning. And this is the average of the ensemble, as we say. So they train the models separately and then take the average. Because if you take the average and then train, then it doesn't work. So basically you just train them independently and then average their prediction. And you see that there's a significant gain from 81 to 84.87% in this simple example of training a classifier on Cypher 100. So the next question is, why does it even work better to match the output of an ensemble, even better than matching the true labels? So the true labels are the true data distribution which we want to parameterize with the neural network. And still, experimentally, it's really accepted that this ensemble of models works better than modeling the exact human annotated, for example, in the supervised case, data distribution. So in the second experiment, they do what is called ensemble knowledge distillation. So they train one single model to match the output of this average that we saw that it had like the average of the ensemble. And it still scores much better than the initial models, even though slightly worse than the ensemble. So between averaging older models, but still significantly better than training the models independently. So this is still a mystery. There is like a huge paper that they published regarding some theoretical explanation regarding this one. Is there a question?
So if we just like increasing the model 10 times.
You train 10 separate models?
But yes, but in contrast to that, we could like train one big model with which had the size of all these 10 models combined. So
yeah, let's say this model is the best model you design for an application. So first you design a model.
So it's not possible to get a better solution using one model.
Yeah, let's say this model, is you first tune the model, the hyperparameters and everything, and you say, okay, this is the best performance I got, and then I repeat the same experiment 10 times. It's not. So basically, instead of training a bigger model, let's say if you have like a bigger model, you can just train the bigger model 10 times and still get the ensembles. This is independent of the choice of model.
What is now the comparison here? Like
this?
Yeah.
So basically, I don't remember if it's cross entropy or KL divergence. We'll discuss about this. So basically, the output, instead of matching, the cross entropy from the real labels, this one hot.
You do it for the ensemble.
Yes, you match the average of the ensemble of the models.
Yeah. So the advantage here is that after all, like if you want to deploy, let's say, the model, you don't need the ensemble.
Yes, you need
you
just
just
one.
use the one that was trained on the output of the ensemble.
Yes, and you still get significant performance improvement over training just one model, like from 81.51 to 83.81 is like a significant improvement.
Yes.
And in the end, you didn't change your hyperparameters, you didn't change your model, you didn't change anything. You just recreated the ensembles and then you match the output of the ensembles. So it's still not so many theoretical understandings regarding this one. I will not cover the theory, but you can check this blog post or the paper. The blog post basically is a larger version of what I described here. So this is still knowledge distillation from an ensemble. And it's still a mystery. So the insight that they provide in this work is that the idea of multiple views, so having one object, like a computer, and taking different pictures, which basically multiple views in the input space of the RGB of the images, can be also translated, or this kind of structure can be seen to some extent from different, okay, here they only consider CNNs. So different CNNs would basically create these multiple view features. So for example, there are many, let's say, high-level features, as they show for the cars. So one model can capture like the wheel of the car, the other will capture the lights, or different parts of the car that all the models are able to classify this image as a car, but kind of capturing different kind of features that correspond to different parts of the image. And this is the idea of, they argue that this kind of views, but in the intermediate layers of the convolutional layers. There's some small insight. So the next question is, okay, we have multiple models and we're going to create them, but so far, okay, let's ignore the application of ensemble knowledge distillation and say we have two models. The next question is like, is it necessary to train a very big model and then distill its knowledge to a smaller model? So the answer is not necessarily. So there is one, it's called Be Your Own Teacher. It's a quite complicated paper, but they were the first one to show this idea that so in the red box they train a big model and then they distill it to a smaller model. And in the second idea, they use the outputs from the deepest layers to train the smallest layers. We will not cover this approach. It's just the first one to show that using the same network, you can have even some small accuracy gain and significant maybe accuracy gain, and also train at least 4 times faster, still with resonance. So here's how they did it. So instead of having a classifier at the end of the network, after each computational block, so for the transformer this would be the self-attention layers, the transformer layers. Here's after each resonant block, they have basically multiple classifiers, and the early layers try to mimic the next layers. So this index C, the sum, refers to different blocks. But in any case, they also match both the features and the probability distribution, the soft target. So if you remove the sums in the red box, this cross entropy, so basically the supervised plus this KL divergence, is what you have to do in the next exercise. So basically, this is what you already know how to do from supervised learning. So here you will have a teacher model that is much better and much bigger than the student, just as a reference for the next exercise. and we will discuss a bit about KL divergence for this way. So when you have the one model and you don't train a bigger model, we refer to this as online knowledge distillation, or otherwise self-distillation. And in the next lecture, we will combine the perspective of knowledge distillation with supervised learning to see more advanced approaches to do self-supervised learning, mostly on images. So this is the alternative way we have seen already. In the last lecture, we talked about this mock approach and the exponential moving average over the parameters. So this is a form of self-distillation. So you have the model and the exponential moving average of the model. So this can be regarded also as a form of self-distillation. Yeah, now it's time to talk about KL divergence. I have some notes. Where is it? So this is the definition of KL divergence. So if you have two probability distributions P and Q, we use this symbol to indicate the closeness or the divergence. And intentionally, we don't use the word distance. Why? Because when you say distance, in mathematics, the properties of a distance is that it needs to be symmetric. While here, here I have a small illustration to show that given this red P distribution and Q, the blue one, the KL divergence even quantitatively is significantly different. So basically KL divergence has two, let's say, directions. So PQ or QP. So I would like to emphasize a bit more because I find it very hard to distinguish which direction should we take. So to illustrate that, we have like a very simple problem. We have this real distribution, which is a multivariate Gaussian with two modes. So each mode is like one valley, if you like, with two means. So this is like, both plots are so far the same. So in the first case, we train an optimal Q. So we parameterize a unimodal distribution. So let's say, not a mixture of Gaussian, but a single Gaussian distribution to model this direction of KL divergence. So P is this distribution, and Q is the unimodal one. And in the second case, we do the opposite. So this is an example from the deep learning book from Ian Goodfellow. And okay, does anybody have a guess? Has a guess what's going to happen? Yes?
So the one is seeking the mean of P of X, and the other one is seeking the mode, so just one of those peaks.
Okay, but which one is the
Left one, I think, is the mean seeking, and the right one is the mode seeking.
Yes, that's correct. Nice. Okay, not the best illustration, but you get the point. So here, the distribution Q tries to capture both modes, and even though here there is no probability density on likelihood assigned, since it tries to maximize both modes of the distribution, so it tries to capture the whole distribution. And in this case, it will focus on one of the peaks. So I will draw randomly just one. Something, I don't know if it's, maybe it should be here or here. Whatever, you get the point that it focuses on only one of the modes of the distribution. So the question is, where should we use, like if we have the teacher, it's like a pre-trained model and the student, which is like the small model we want to train, or even if it's the same size. Should we use one or the other? So in supervised learning, it's quite clear that we want to capture basically the whole data distribution and not just one of the modes. So here I'm drawing I'm mathematically describing the connection between KL divergence, which is this term here. And if you just decompose the two terms, this is the entropy of P, and including the minus, this is the cross entropy, P of Q. So let's say in the supervised case, which one is the teacher, P or Q? You should be able to answer this question easily. So P and Q, which one is the teacher, basically the data distribution in supervised learning where you have this one hot distribution? Nobody? Which one?
P.
Yeah, P is the one hot distribution and Q is the prediction of the model. And what happens if you take the gradient here? So if you take the gradient with respect to Q, this term drops out because there is no parameter to be optimized here. There are no gradients with respect to basically to the data distribution in self-supervised learning. I hope it's clear. So which one is the one that you should use if you want to do knowledge distillation? Should you use the student or the teacher? So in general, it's not clear it's basically what you want to achieve. There's not always one answer. So they also argued in this example in this book that sometimes you may only want to capture one of the modes and this would make sense, and sometimes you want to capture the whole data distribution. So experimentally, in this exercise that you will implement this week, I didn't find like a great difference between the two approaches, even though I didn't spend so much time. But the point is that when you have like a randomly initialized student and the trained teacher, which one of those distribution in the beginning are more sharp? Any ideas? You have a teacher and a randomly initialized student, and they have two probability distribution. Which one is the sharpest one? More sharp, it means
More peaky.
more. Yes. The teacher has a sharper distribution because the student initially would be almost uniformly distributed among these different classes. So I want to emphasize that basically when the teacher is, let's ignore this part. So when the teacher is here and it has this initial distribution like that, it will not be one hot, but it's usually tends to be quite sharp and confident, even though it's not exactly one hot. It may have different probabilities to some other classes, whatever. But in general, it's quite confident or sharp, whatever. So basically, I want to emphasize that since P is here, if you use the teacher here, all these parts will drop out, and the student will try to match this peak. So this is some sort of intuition. And in practical terms, in the exercise, I didn't find a great difference, but maybe you can experiment with both and tell me which one works best for you. So the next thing to discuss is how can we achieve. So far we talked about the logit space or the probability distributions, but this is not the only way where we can pass the knowledge from different models. So for some pre-trained models, we may not even have the different heads that point to some number of classes or clusters, whatever. So this is one approach where basically you use contrastive learning. So you take the features from the student and the teacher, and you apply contrastive learning. So what does contrastive learning do? It pulls together in the feature space positive pairs. What is a positive pair? The features of the student of the same image and the features of the teacher of the same image. So you pull them together and you can train a student network even without this idea of cross entropy and modeling the soft targets, even if you don't have the head in general. So we have covered the last two lectures, and I told you like contrastive learning is quite general. So here this is an example where you can model even an ensemble of teachers, and you just apply. So basically for each pair, so student is like the central view. So you can consider everything as a view. You can say view 1, view student. Sorry, what? So view teacher 1, view teacher 2. So in general, it's like the ensemble of different random initialized models. And each time you take the pairs. So this would be a positive pair in a contrastive learning. That would be one loss function in this L critic. So I is the index of the different teachers. And this is just the contrastive learning objective we have seen so far. So instead of taking augmentations of the same image, we have these ensembles. So this is like the features. So view from teacher 1 is the features from the first separately trained model. And then the second, and then the third. And then you average, you sum all those together, and this is the supervised objective. So just want to show you, just in the case when you don't have these heads and you want to train directly on the features. And this, in this paper, it has worked slightly better even with the cross-entropy distillation. Here they applied this idea in a specific modality. I will move on. They just passed the information from a pre-trained ResNet on image to a small CNN that was the part of the encoder in a segmentation problem that accepts depth images. And they had some small improvements. So this CRT, but we will not emphasize on that. So this is the summary of all this part. So model ensembles can boost performance. With self-distillation, we don't always require fixed and large teacher. This is what we will do in the next lectures in self-supervised learning. And you can capture multiple views in the feature space with these model ensembles. This is a paper from Microsoft. And lastly, the distillation can be implemented in the feature space, for example, with contrastive learning. So this is the last part where I want to bring these two things together. So we talked about vision transformers, knowledge distillation. So there are a lot of approaches that refer to vision transformer based distillation specifically for vision transformers. So this is the first one. Maybe I will need to draw something. So here you have the path-based projected tokens. Here you have the class tokens where you do cross entropy in the output with after this blue corresponds to a small head, it's a small MLP or a linear layer and softmax. And then the idea is that we can add as many patches or tokens as we want. So let's add one more token. So this is just a randomly initialized vector. They call it distillation token. Just trainable randomly initialized vector. And then let's take the output after the transformer. So during all these self-attention layers, all these tokens communicate with each other at each transformer layer. So in the output, let's take this these features from this distillation token, and let's try to match the output from another pre-trained model, so another teacher. So this is only possible when you have a vision transformer architecture, because you accept in the end just one sequence. And the same way in natural language, you have the start of sentence, end of sentence, segment level representation, masking, tokens, and all these things. Here you can just arbitrarily represent one token and try to match its output from a teacher. So they have shown that it works quite well when you have a pre-trained teacher. And they also saw that in this case, as opposed to what Hinton showed in 2015, it's better to take the hard targets from the pre-trained teacher, no matter if it's a CNN or another transformer, and use it to match this probability distribution. So both objectives are cross entropy here. So one is the supervised and the other is from the teacher. Okay, here are the numbers. So the main result is that hard distillation, as it's called, so just to take the one hot distribution over the prediction of the teacher, it works better just in this case. That's why I told you there is no one solution in general. And second, that distilling, basically modeling the output of a pre-trained CNN with a vision transformer works sometimes even better than training just with a supervised objective. And here are some improvements. So this is ImageNet, and these are like the different transformer variants, so you can just take the base vision transformer as a reference. And you see here, instead of just doing cross entropy, you add this and you have 0.4% improvement. And okay, in parallel, I would like to emphasize that this 0.4 sounds trivial, but if you consider that ImageNet has like 100,000, let's say, images on the test set, maybe 50,000 or 100,000, this 0.4% is something like 400 images are classified correctly in addition to the previous model. So this idea was used later to kind of model either the learned features, invariances from learned features. So we use again this distillation token, but now they use it in another context. They try to match the output of a model that is pre-trained or a very unique data set that you are unable to classify the image based on the texture, and you can only classify the image based on the shape. So this is the data set, how it looks like. It's called stylized ImageNet. So basically they remove all the features that relate to texture by creating these additional samples with different computer vision techniques. So the only way you can classify these images correctly is by learning shape-based representations. And then they took the output of this model of a trained reset on this stylized ImageNet to train a vision transformer. So basically this is another technique in representation learning in general where you want to introduce some additional invariances or model inductive biases from other models to have like the desired characteristics that you want. Okay. And okay, now we will talk about the state of the art, which is basically how can we efficiently distill a very large vision transformer to a small vision transformer. So the hint here is that we are not leveraging all those representations, all those token-based, patch-based representation in a vision transformer. We only take the classification token So even though this classification token communicates with all the other tokens, there is nothing happening with these outputs. So basically, what if we additionally match not only the classification token, but also the patch level outputs, the patch level output representations from the transformer, and this is what the state of the art is doing. So instead of just taking the output of the CLS token and do cross entropy, they have another head for both models. So this can be also trained. This can also be an exponential moving average or a large model. It doesn't matter. This is the teacher in general. It can be also a huge, bigger model. So you just pass the output from another head that is responsible to have like probability distribution over the patch-based representations. So even though in language you can map all the words in a specific vocabulary, so let's say 100,000 words, so you can intuitively think that here we map all the patches in these type of clusters. So this cross entropy is happening in some high dimensional space, like 10,000. So basically, the model has to classify all the patches, no matter how diverse they can be, in one of those 10,000 classes to apply cross entropy. And we will talk about this more in depth in the course, but this technique in general is called masked image modeling. If you want to do self-distillation, but if you just want to do distillation, you remove the mask parameter. Here you have the teacher. Let's consider the blue. So you take an image, you take an augmentation, you ignore this part, you have these two sequences. So this is the student we want to train from scratch, this is the big teacher. And then we pass those blue views from the head. And then we match with cross entropy all these patch-based representations, and we take the average, we take the gradient. And these are some results, so they can pass the model from 1 billion parameters to 300 billion parameters without losing any performance, almost nothing. And I went a little bit fast, so this is the summary. The transformers are much more flexible because we don't work directly on the image space, but we project these patches, and in the end we have some tokens, and then we can add additional tokens, which enables us to do more tricks regarding distillation and different techniques that we will see through the course, like masking and everything. And masked image modeling helps us to distill the model from very large networks much more efficiently and faster, and it's basically the last 2 years is like a widely adopted technique in computer vision. And I also showed this idea of passing inductive biases or desired characteristics from other networks, such as this resonant trained on this stylized ImageNet data. Yeah, that's it from my side. Any questions? Okay, that's it for today.